Okay, in this second screencast, we're just going to do a few examples of calculations using this graph. So let's say, to begin with, we want to work out the acceleration of section A. Alright, so we know that acceleration is the change in velocity over the change in time. Now remember, change means final minus initial. So that's going to be the final velocity take away the initial velocity divided by the change in time, which is the final time take away the initial time. And so we can see in section A that the final velocity was 3, the initial velocity was 0. The final time was 3 seconds and the initial time was 0. And so it's going to be 3 take away 0 over 3 take away 0, which is 3 divided by 3. So it's 3 meters per second divided by 3 seconds. And so the answer is 1 meter per second per second. So it's 1 meter per second per second. Now that means, what that actually means is it's increasing its velocity by 1 meter per second every second. Now normally we would write that as 1 meter second to the negative 2. So meter per second can be written as ms to the negative 2. Alright, if we now want to have a look at section B, the acceleration in here, it's the same deal. It's really, and by the way, I had to make this explicit, but the acceleration is the gradient of the graph. This is the gradient of the velocity time graph. And so we can state that the acceleration for any section of the graph, or the average acceleration I should say, is equal to the gradient of the graph. Gradient of a VT graph. We'll get to instantaneous acceleration very soon. At the moment we're talking about the average acceleration over a period of time. So the gradient of VT graph is the acceleration. In section B, once again, all we need to do to work out the acceleration is to work out the gradient. So we need the rise of the run, or alternatively just your final velocity and your initial velocity. Let's use this method here since we've used it initially. So here, the initial velocity was 3 meters per second. The final velocity is 6 meters per second. The initial time is 3 seconds, and the final time is 4 seconds. And so the acceleration for section B is going to equal the final velocity take away the initial velocity divided by the final time take away the initial time. That's going to be 6 take away 3 divided by 4 take away 3, which is going to equal 3 over 1. So that's 3 meters per second over 1 second. So the answer is 3 meters per second, or write that as 3 meters per second to the negative 2. And so this is telling us, of course, that it's increasing its velocity in the easterly direction by 3 meters per second every second. Let's have a look at section D. Now remember, we said in section C that the acceleration is 0 because the gradient is 0. So in section D, once again, actually what I'll do, I will clear that, create a new thing. Okay, for section D, we have the acceleration in section D. Once again, it's the same formula. It's change in velocity over the change in time. So it's going to be the final velocity, take away the initial velocity, divided by the final time, take away the initial time. And if we look at this section, I'll just draw some guidelines here so I can see what we're doing. So, okay, so the final velocity for section D was 0. Remember, that was 0. So it's going to be 0, take away, the initial velocity was 6. So 0 take away 6, and the time, the final time was 8-second mark, or 8 seconds. The initial time was 5 seconds. There was your final time, and there was the initial time. So it's 8 minus 5. And so it's going to be negative 6 over 8 minus 5 is 3. So that ends up being negative 2 meters per second per second. So what is this telling us? This is telling us that it's increasing its velocity towards the westerly direction at a rate of 2 meters per second every second. Okay, so and of course we could write that again as negative 2 meters per second squared. Now, what students often get confused with here is because they think that the graph is now heading downwards, that the object must be moving in the westerly direction in this case. That is not the case here. Okay, because even though the gradient is negative, it's telling us that the acceleration is negative. It's certainly got a negative acceleration, which means that its change is heading in the negative direction, or it's changing towards the westerly direction. But whilst it's in section D, it's still travelling in the easterly direction. It's just slowing down, okay, slowing down till it reaches the 8-second point, and where for a split second it stops, then it starts travelling in the opposite direction, which is west. Okay, so there's just a couple of examples of how we can use the gradient of the velocity time graph to work out the acceleration. If in the final screencast, I'm going to show you how we can actually work out the displacement by using a velocity time graph.